Hi, and thank you for joining us on this video. We're here to talk about actually architecture dependence when working with GPU technologies. Oregon State University Center for Genome Research has worked hard with many different groups on implementing GPU technologies, and we implement these in ways that help us really change the scope of work that we can do and remove bias. This demo will be able to go through multiple algorithms where we can see how architecture dependence really plays a role in our use of these GPUs. Some of them will be streaming data through the GPU, some of them will do transactional data, some of them will put the data directly on the GPU and just let it run. And we really want people to understand it's not the GPU sometimes with how the data is processed. It's really the architecture we plug that GPU into. The hardware that we're working with here is actually two main pieces of equipment. One is an IBM POWER9 AC922. It can support up to 6 GPUs. And right now we have it with two processors in it, 2.2 gigahertz, and ultimately we have two VMs set up, one with one NVIDIA V100 32 gig GPU and one with two of them. That allows us to test both single GPU interaction and GPU to GPU interaction. On the x86 side, we have a standard box that's used for GPU processing. It's one that can actually hold about 8 GPUs. In this case, we have the exact same GPUs as above, the NVIDIA V100 32 gig. We have the exact same speed processors. And this is generally the style of configuration that we find groups purchasing for research computing on the GPU side when they're not looking at the IBM. And so these are the two types of equipment we actually purchase in the Center for Genome Research to do a lot of our AI, deep learning, machine learning. And we really wanted to show people how these different pieces of equipment interact. We understand that there are some new technologies coming out on the x86 side that involve an SMX2 bus. We're going to talk about that a little bit. We have some data to show from a DGX2 in here as well. And we want people just to be aware of how architecture plays a role with GPU. All the GPUs we use are NVIDIA GPUs. We believe strongly in the NVIDIA GPUs. We work closely with NVIDIA. We really think they come out with some of the best GPUs on the market. And we really enjoy working with CUDA. It's a very strong language and really helps us change the work that we can do. We will be playing each one of these demos one after another, and each one of them will show us something different. Users can gain access to this by registering online. We will put the URL in the information below, and they'll be able to select a slot. We have dedicated hardware to this demo, and we're allowing users to isolate themselves on that hardware so they're the only users and they can see pure performance. We've tried to optimize the code everywhere we can to ensure that we get the best and fastest processing both on the POWER9 side and on the x86 side. On the power side, we found that being able to leverage Watson machine learning gave us quick and fast optimization that we didn't actually have on the x86 side, where we had to hand compile TensorFlow, Keras, and things like this, Python, Bazel, and things like this to get the actual performance out of the machines as we expected. And you can see performance differences when you hand compile. I think it's important that users get direct access to the hardware. Users can register, they'll get 2-hour slots. We appreciate you watching this demo, and enjoy. Okay, the very first demo we're going to run is called Avian CNN. It was created at Oregon State University, and it's been a research project supported by the Forest Service. This convolutional neural net leverages Keras, TensorFlow, Pandas, and OpenCV. And let's go ahead and go towards the demo. This demo is actually here to run the algorithm that helps us identify owls in the forest using sound. So we have recorders in the forest. They sit there and they record the forest and allow us to then break the data up and then identify owls. Right now we're finding about 11 different species. of owl, and we're finding, I think, 2 different species of other mammals. Right now, this algorithm generates about 150 terabytes to 200 terabytes of data every season for about 1,500 recorders. We'd like to scale up the number of recorders and increase the amount of data we can process. So in this case, we're going to be able to run different machines, in this case racers, against each other. On the left-hand side, we're going to pick an IBM POWER9, the 2.2 gigahertz processors. It's going to have one NVIDIA V100 32 gig card on it, and on the other side we'll pick the Intel setup that holds GPUs, and in this case we'll also pick one NVIDIA V100 32 gig. So in this case we have the exact same GPU, just different machines running that GPU. Okay, and so as we click Run Demo, we can see that as things get started here, we have some timers, we have some plots showing us some throughput, and then we have the command line output. So as you immediately look, you can see that the left-hand side, where the IBM POWER9 machine is able to immediately get started, push the data out onto the GPU. And that was a really important thing for us to notice, is the interaction with the GPU was so immediate. Ultimately, this is pushing a large amount of data through the GPU, and so what we want to see is as much throughput as possible. Both of them are going to use the same amount of memory and roughly the same amount of GPU. In this case, the GPU load is a little bit higher on the POWER9 one, because we're actually getting more work done over time, and so it's going a little bit harder. It's actually moving a little bit more, and you can immediately see that there's already almost a 2x speed up on the left hand side with the AC922. So we really appreciate that speed up. And that speed up's on top of the lag that we see getting onto the GPU. So as we get onto the GPU, there's that initial lag, and then just the pure runtime, we're seeing almost a 2x speed up. And so that's really important to us. This algorithm ultimately just records the forest, and so we don't know how many sounds are going to come to us as we look through that sound data. We don't know if it's going to be hundreds, millions, hundreds of millions. We really don't know, and as we increase the number of species we find as well, that's going to increase the number of spectrograms that we ultimately have to send through the GPU. And so we can only see how this process is going to increase the amount of data that we go, both in terms of the recorders and in terms of the amount of species, and it's dependent upon how many times that they actually make calls in the wild. And so our hope is to be able to passively sample the forest and even potentially monitor individual animals moving through the forest and how that operates passively, just using sound. So as you can see right now, we only have about a minute and a half left or so, minute and 48 here on the left hand side, and you still have about 5 minutes, 4 minutes 50 seconds over here on the right hand side. And so that's the speed up that we've seen, is that allows us to really change the amount of data that we actually process through. We can actually put more jobs if we want to by changing the memory usage and put multiple jobs on an individual GPU in this case. And if we're able to do that, we'll see even a more dramatic return, because each one of the jobs will have that same return. And out of a single GPU, we may get 4x return rather than just a 2x. And so we're going to let these go ahead and finish, and we'll let the video here speed up so that way we can get to a quick end, and ultimately it'll generate some output, and we'll talk about that. Okay, so the demo has completed, and as you can see, it's not quite a 2x, but it's a tremendous performance increase as we went through. And there's a report that actually comes with that. And so it's important to remember that the machines in this case are the only difference. It's running the exact same code. We spent time verifying the optimization on both sides to make them run as fast as they possibly could. And we really feel like this was just a consequence of moving data across the bus. Our other demos will test more of that concept and see how that plays out. This one really showed us that there was a delay initially interacting with the GPU, and then the throughput on the GPU was not as good on the PCIe side, and so we really saw that performance increase with this other piece of equipment, the AC922. Thank you. We will pick up on the next demo here shortly. Okay, for our second demo, we're going to be running this Plankton CNN. The Plankton CNN was built utilizing the sparse convolutional net from Facebook and OpenCV and CUDA. This one actually allows us to identify plankton in the ocean utilizing video. So we take and collect video at the ocean, just dragging the video camera behind the boat. We then take that video, we segment it every time we see a spot, and we take the spot, put that into a picture. Every time we see that picture, we take and process that through the GPU, through the CNN, and we can identify 160, 167 maybe different types of plankton, and that helps us understand ocean health. Okay, this algorithm right here has to process about 100 terabytes of data every week at sea. We go out several times through different parts of the year, and now we have several groups doing that. So as we scale up, the amount of data that we can process becomes the limit to our research and our analysis, and it's important that we can get through the data quickly. This algorithm that we're going to run is a little bit different in terms of the fact that it shows us more of a transactional aspect of how transactional data works. In this case, we have to geolocate all of the data, and so what we have are small batches of images based upon geolocation, and we can do lots of these small jobs on a single GPU at a single time. And so what we're going to do is investigate with this demo the aspect of going on and off the GPU in rapid succession and the consequences of doing that based upon architecture. Now again, we're going to run a single AC922 with a single NVIDIA V100 32 gig GPU, the exact same GPU on the Intel-based box, just a different bus architecture in this case. And we're going to go ahead and start this demo. And again, we'll be able to look at the various features, like the amount of GPU memory, the throughput, and then the command line. And what's really important to watch on this one is that the amount of transactions that are going on the left-hand side compared to the amount of transactions on the right. Now, in this case, we don't utilize all the memory and we don't utilize all the CPU on an individual GPU. And so we can actually put sometimes 3 to 4 jobs on an individual GPU. And so these transactions and how long it takes to do these transactions becomes the tail of the tape to us. And so right here, this is one set of data, one set of transactions, one run going, and we can see that we already get a 2+x return. This one is seen as much as a 3 to 4x return on an individual set of jobs going on a GPU, and we can put 2 to 4 jobs on an individual GPU. So there's a tremendous return per job, and then the number of jobs we can do really starts to exponentially increase our return. And this again is about getting on and off the GPU. These are small enough jobs that they fit on the GPU easily. Once the job lands on the GPU, the work is done in about the same amount of time. The difference here is really moving on and off, and that's the bus speed. And so this is how the GPU is interacting with other parts of the infrastructure, other parts of this architecture on this individual machine. So we have to move the data sometimes across from large spaces, across NFS. Just depends on where the data is. Now, in this case, all the data is local, but it's always been a situation where bus becomes the bottleneck to some of these machines like the AC922 for us, not the bus architecture on the individual machine or the GPU. The GPU seems to be able to start handling the workload. Again, we love the GPUs, and this is the exact same GPU. We run all NVIDIA GPU. We think they're some of the best GPUs out there. We think they're some of the best for data processing, and we just want people to understand that where you put your GPU changes the way that it interacts. And we know that there's some other technologies coming out on the x86 side as well, and that it's important to leverage those as much as possible. We will have some data here at the end about the DGX2, which runs a non-PCIe bus, the newer style of x86 NVLink. It's not NVLink, it's SMX2, but it is a much better bus than this, and we want to acknowledge that, and we can still show some data around that. The AC922 still somewhat outperformed the DGX2 in this case, even because of these transactions. Again, getting on and getting off, there was a greater cost on the DGX2, and some transactional data becomes important. As we look at transactional data, if companies are trying to do transactions, they can do more transactions on this box over the same period of time, and that could actually translate into more dollars. For us, it translates into more data, changes the scope of work we can do, and removes bias. And that's really what we're after here. We need to be able to process this data quickly enough that we can have the boat go back out and redo some more work for us. And we want it to do as much as possible. So this one is actually finished on the left-hand side at this point, and the right-hand side will take some time. We're going to go ahead and let the right-hand side go. We'll speed up the video again, and hopefully that will complete quickly. As you can see, there's a greater than 2x return. The reason that there's greater than 2x return is that the transactional aspect really slows us down. You can see the blue bar. We got a little bit of a wait, but we're going to wait it out and speed up the video for you. Okay, thank you. Okay, so there we go. We're done. We can actually see that the performance is there. Again, we want to remind people that these were really small jobs. This was not a lot of data, and the data fit easily on the GPU. This was really us trying to leverage this algorithm to understand the consequences of transactional processing and bus architecture. Not GPU, but bus architecture. Remember, these are the same GPUs, just plugged into different machines. It's really just where we put the GPU, not the GPU. The GPU can do amazing work when leveraging the right architecture. We will see another demo here shortly, and that demo will cover a different aspect. The aspect we'll look at next is one where each individual job fit easily onto the GPU. Let's see if we didn't have to do transactions, what the consequence will be. Thank you. Okay, we're going to get started on our third demo. This demo is going to look at this algorithm called CASA, which is a genome sequence alignment algorithm we wrote here at Oregon State University. This one leverages just CUDA. Again, these are NVIDIA-based GPUs. We really like CUDA. CUDA was a great technology for us to write this in. It was super fast. This algorithm does a Burls-Wheeler transform, which is a very well-known algorithm for doing genome sequence alignment. We do lots and lots and lots of genome sequence alignment throughout the scientific community. And right now we're spending a lot of CPU cycles doing that. The reason is that there aren't many algorithms right now that work on the GPU. And one of the things was interacting with data across the GPU. Now in this case, we've taken time to make sure that the data sets that we're going to work with completely fit onto these GPUs. And we're going to be looking at this algorithm in context of if we were able to put everything onto the GPU, get it on there at the same amount of time, should the GPUs finish in the same amount of time? And so really this is a test of if the architecture wasn't in play and we were strictly on the GPU, how would that come and how would that look? Again, we're going to stick with the one AC922 on the left-hand side with the one NVIDIA V100 32 gig. We will pick the one Intel on this side, the x86. Again, one NVIDIA V100, so we have one NVIDIA V100 on both. When we run this one, it'll go very quickly. In this case, it will be able to load the data pretty quickly. It doesn't leverage much of the memory in this case. We've picked a very, very small data set. And you can see there's a little bit of a lag getting out, a 1 second or so lag getting out on the x86 side. And that's that standard lag we've always seen. That second's not going to cost us too much in the overall processing because we're going to spend more time processing in this case. This is more analogous to doing simulations on the GPU. People who are doing simulations on the GPU, there's really no need for a bus architecture that's moving data. And so the AC922 and the Intel really play out pretty much exactly the same here. And that's what we really wanted to show and see was that really was the case. That when you basically put your work onto the GPU and you spend a great deal of time sitting on the GPU, that initial load time is nullified and it's not going to actually be seen. We can actually discount that in terms of just interacting with the GPU a little bit. And we're going to finish in about the same amount of time. So as we get close to finishing here, these are real close to done. We'll see them actually finish in about the exact same time. In this case, the x86 won. Okay, and so they both actually finished in 74 seconds. The x86 just got the green light first. It finished a little bit before, and that's what we see. We see in this case the ability for the devices to act about the same. Really, no consequence getting out there. And when you're focused on long simulations, buying GPUs in any context is going to be a win for you. Getting yourself onto those GPUs, we found CUDA has been a very good language for that, and you can see it goes very fast. We were able to do a small data set in this case, but one that was still meaningful and gave us information back in less than 2 minutes. And so the speed up was about 20 or 30x from an actual CPU job. And so that GPU return is tremendous. And in this case, it really didn't matter what the bus architecture was. We were going to get that return on either side. And I think that that's what we really wanted to show. Thank you. We will start up another demo here shortly. Okay, for our fourth demo, we're going to do the SETI signal classification. This demo will utilize TensorFlow, OpenCV, and CUDA. The demo actually processes image data that comes from spectrograms generated from radio signal data. In this case, we're going to be really focused in on how the GPU to GPU interaction occurs, and when we run on a single GPU, it should take about the same amount of time, but once we start to scale up and do two GPUs, we really start to see that difference start to occur, and that's what we want to look at here. So in this case, we're going to be running on an IBM POWER9 AC922 with two NVIDIA V132 gigs, and then we'll also run the Intel Xeon with two NVIDIA V132 gigs. Okay, so it's two GPUs against two GPUs. Just different interconnect between those GPUs and how they interact. Alright, as we get going here, we won't see a lot of command line output, but we will see different types of interactions happening on the bus and the CPU side. So always a little bit of a delay getting started on the PCIe bus, as you can see. But once we get started, that's really not going to affect us. It will run for about the same amount of time on a single GPU, and it will run for a long period of time. So that initial cost of getting onto the GPU is not too bad. It's not really transactional data. It really just sits on there, and it's going to go GPU to GPU. So we're really going to be looking at that interaction between the two GPUs. Our hope is that we do see a speed up when we start going here. And at the beginning, you're really not going to see those bars, the blue bars, change that much in accordance to each other. But as we go further and further and further, we start to see that change and that return start to come into play. Now, the runs that we generally do with two GPUs are really long standing runs, and we're trying to invoke multiple GPUs to reduce those runs. And what we see is we can get that with the NVLink. Now, we know on the x86 side there is some other types of buses coming out, like the SMX2 bus, which is a similar style of NVLink where we can talk GPU to GPU. The NVLink on the AC922 seems to be not only GPU to GPU but also CPU to GPU, allowing us to start taking advantage of system memory for jobs that couldn't fit onto the GPU per se. So we're going to let this run. It could take about 15 minutes in total to run. We hope to speed up the video here for you, so we will talk to you at the end, and that'll reduce the time. Thank you. Okay, so the demo's done. We ultimately see a small speed up from actually going GPU to GPU on the AC922 versus the GPU to GPU on the PCIe. Now these were a small amount of interactions, and as we scaled this data set up, it keeps getting further and further ahead. And so right here we get a 1.2x increase. We ultimately start getting up to around 1.5 after we've gone for about 3 to 4 hours. And it keeps going like that. And so the more you do this, the better the return in the end. And that's really what we want to show people, is that GPU to GPU is going to be where we're headed. So that way we can reduce run times, training times, and different things like that. Thank you very much. Okay, welcome. Let's start our fifth demo. In this case, it's going to be looking at the sysbench benchmarking down here. Now, we recognized very early on that machines that were being purchased for GPU actually sometimes had to do multiple things, and that people were putting GPUs on main processing machines that did actual CPU processing as well. And so the machines actually had to be dual natured, and in some ways bifurcate the actual workloads. And so in this case, we see some workloads going CPU, some workloads going GPU, and some workloads now going CPU GPU. And so we really wanted to show what the consequence of architecture with CPU interaction was. And so this one does not leverage GPU at all. It just looks at CPU and the CPUs that we run on different pieces of equipment that we run with GPUs, okay? And so in the yellow box, we see a benchmark where we've done 4 threads. We've task set this so it goes onto a single socket. We tried to get as much performance as possible. We ran the exact same versions of sysbench. We tried to make this matched up as much as possible, and this did as many operations as it possibly could within a certain period of time. In this case, the POWER9 processor was astounding and continually beat out the processor we had on the main PCIe-based GPU server by about 4x, and then on the DGX2, where we had platinum Xeons that were even a little bit faster, they were 2.7 versus our POWER9 that was 2.2. We still got a 3x performance increase just on the CPU side for threading. And as we continued threading up, we actually found more and more performance increase. We just wanted to keep it small and fair based upon the number of threads and things. And so in this case, we really found a tremendous return on the CPU side on our POWER9 box. And all the POWER9 boxes we buy, regardless if it's an AC922, we just put the AC922 in front because we buy a lot of them and we use them with our GPUs. But we found that they had a tremendous amount of capability on the CPU as well. So as we went down into the blue section, this was our memory test. And the memory test, the Intel boxes won every single time. And we really appreciated the fact that the Intel memory bus was really strong and worked very well. We think that there was some optimization associated to sysbench and some libraries on the Intel side that really helped keep that speed and throughput on the memory side. So the Intel absolutely wins the memory every time, and as you can see, the DGX even does better than the standard Xeon. They were all running the same type of memory, and they were all running the same speed of memory. So that's important to realize that this was bus architecture again that played a role here in how the boards and things were laid out. So the DGX2 really had the win here for us. And then as we moved on down, the green section has the throughput, the actual I/O throughput, and this is where we used SSDs. So first we had SSDs on the Supermicro machine where we put lots of GPUs, and we had those SSDs configured the exact same. And so we saw a tremendous I/O throughput, and this is the value we've been getting at for us, is moving data across that bus. We can move a lot more data a lot faster, which translates into getting onto that GPU faster. We thought, we needed to test the DGX2, so we also had NVMEs. The NVMEs on the AC922 were CAPI enabled, The DGX had NVMEs that were standard NVMEs. Both were configured in RAID 0. As you can see, the AC922 again won on the I/O, even though it had a little fewer NVMEs. We really find that the I/O bus on that AC922 is what we're after. It helps us actually change the throughput of our data going across the GPUs and almost anything else we interact with. So if you're pretty much leveraging CPU, you probably want to be looking at a POWER9. If you're leveraging memory, you probably want to be looking at x86, Intel, probably DGX. And if you're leveraging I/O, you want to go back with the AC922 and leverage that CAPI bus and stuff. Okay, let's go ahead and run this demo. We're going to let it go ahead and run. It'll generate the exact same numbers that we just showed you, but it was important to be able to show you the numbers early on. Okay, so we run the exact same code. It's pretty much the exact same version, and we're able to see that they run. They will go through, run different threading counts, see the amount of I/O operations. It'll do the I/O, the memory, and then the I/O. And so through this test, we recognize that there are aspects of different machines that are better. And each one of the machines does different things better, and we should have a heterogeneous environment to help us get through our processing, so that way we can get it through the best possible way. These run in the exact same amount of time, and you have different amount of operations that can be done on each one. In this case, the output is the output you see in that table, and so the table is our actual information, and the column of throughput is what we really want to look at. And again, thank you. We appreciate your time. All right, thank you for watching our demo videos. I hope that we've helped you understand how our architecture dependence in GPUs works, and hopefully you can make educated purchases when trying to buy hardware to do certain types of deep learning, artificial intelligence, machine learning, whatever that is. We wanted people to have an opportunity to see what the DGX times were for some of these algorithms compared to the IBM AC922. And so here they are. This is the exact same code again running on all these. And the times here that we see are when we run on NVMe, RAID 0, we see a little bit more speed up on the POWER9 because we came off the SSDs that were on the machine when we were doing against the SSDs on the Intel side. The DGX2 had the NVMEs, so we went ahead and ran the NVMEs. The NVMEs on the POWER9, what we call CAPI enabled, a coherent accelerated processor interconnect. And that really speeds up the NVMEs. We found some greater throughput over there. We've shown that in some of the data earlier in some of the videos. And so that's where we found drop. CASA, of course, dropped. Everybody dropped because of that NVMe and the I/O interaction. So we really want people to understand that interacting with data, it doesn't matter to us where we go. Right now we want the fastest. We want to be able to reduce those times as much as possible. The DGX2 really helped bring that to the table. The DGX2 seems to be far more comparable to the POWER9 setup and far more online. The times that you got there are very similar to the times that we got on the POWER9 when we were running on the SSDs. And so what we can see is that the speed up on the POWER9 compared to the DGX2 is really coming from the CAPI bus and from how the NVMEs and that CAPI bus are interacting. And there's a lot of different things we can leverage in that CAPI bus, but in this case, it's really just moving the data faster for us. And so the DGX2 is performing well. The POWER9's performing a little bit better, I think, because of that CAPI. And so, again, we appreciate you giving us the time. We want you to ask any questions and feel free to sign up to get access to the demo.